All right, we're going to start our second unit on derivatives today, which basically continues where we left off with limits. So if you remember when we did our limits, the goal of a limit was to figure out what the value was as x approached a certain number. And then where we left off, there's a little typo here, we don't need this 1 on there. Where we left off was we used this limit formula, the limit as h approaches 0. That helped us calculate the slope of a tangent line at any given place. So what we're going to look at now is we're going to say, is there a better way to do slopes without using this formula? So differentiation is the process that we use this limit formula, but we kind of use a shortcut. So limits work, derivatives and differentiation will do the same thing, but a lot quicker. But we're still, because it is based on limits, we still have to make sure in terms of our graph, if we're trying to calculate the derivative at a certain location, it has to be a continuous graph there. So if I told you find the limit when x was 2, we're okay because at 2 our left-hand limits and our right-hand limits are approaching the same thing. But if I say find the limit at 1, it's not going to exist because that's our asymptote line. So just like we did with limits, derivatives are the same thing. In this case, the derivative would be possible at every location except for where that asymptote line is at 1. So what we're going to do now is, how does this actually help us? So derivatives and slopes of tangent lines are actually quite powerful in terms of math and science. What we're actually calculating from a graphing perspective, remember, a slope of a tangent line is just what's going on at that specific location. So if I gave you a curve like that and I say calculate the slope at this tangent line, we're figuring out the slope of that red dotted line I just drew. But more importantly, that slope is giving us an instantaneous rate of change. So from a graphing perspective, it's just the slope. But in other areas, it's giving us how quickly those two variables are changing compared to each other. So if this was a distance time graph, what we've just calculated at that specific time is we've calculated the speed, the instantaneous speed of that location. If I made it a velocity time graph, it would be things like acceleration. I could make this money over time, and then that would tell us how much our value is decreasing. So let's suppose this was like the depreciation of a truck or something like that. So these things change depending on the variables, and that's why we're going to change it up a little bit. So instead of writing it as just slope as m, we're going to write it as dy dx. So the change of the y coordinate versus the x. So if I change the variables, like if I made this velocity and time, our slope then would be change in velocity divided by time. Okay? So from a graphing perspective, a negative derivative is going to mean we got a negative slope or a negative change. Positive, obviously positive slope or positive change. If we get a slope of 0, that means there's no change at all, or in terms of our graph, it's stationary at that particular moment. What Newton did was he changed the formula around a little bit. So like I just wrote on the previous page, instead of writing slope as m, we're going to think of it as change in y over change of x. And because we're going to call it derivatives, he used small delta instead of capital delta. So the triangle is delta. This d actually looks a little bit different in Greek letters. It's kind of tilted a little bit. But to make it easier, we just write it as dy dx. So the dy dx is just going to represent our slope if our variables are x and y. And like I just said, if we change the variables, if I gave you some sort of equation that was volume equals pi r squared h or something like that, we could do the derivative of volume with respect to h. Or we could do the derivative of volume with respect to r, or whatever. So we'll get into those kind of scenarios a little bit later on, but that's kind of why we write it as dy dx, that we can change our variables quite easily. Newton also kind of liked to use a prime notation. So it's different guys. Leibniz kind of like dy dx, Newton likes prime, or vice versa. It really doesn't matter. They're just different ways of writing it. So for example, let me clear this off here. If our equation was, oops, what did I just do there? If our equation was, let's just do a simple one. Let's say it was y equals 4x minus 3. So and it just sort of depends on how we write the equation. But if I gave you y equals 4x minus 3, we could do our derivative as derivative of y with respect to x, because that's the variables we're working with. We could also write it as y prime, so the prime basically means the same thing. A lot of students like the prime notation because it's pretty easy, but the problem with the prime is we don't always know what the variables are. So another way of doing it is, instead of me writing it as y equals, remember I could write it in function notation. So now we know we have a function, so we could use the prime notation and then put the variable in brackets. So f prime of x kind of is the same thing as dy dx, just a little bit different way of writing it. So all three of these are totally acceptable when we're dealing with derivatives. And we use them interchangeably. Some kinds of questions it's better one way, other times it's a little bit better. Okay, so let's do a question kind of the old way, and then we'll see if we can figure out a pattern. So if we take our equation, y equals x cubed, and our goal is to try to figure out the slope of that equation at any location. So this is slightly different. In the previous unit, we figured out what the slope was when x was 1, or when x was 2, or something like that. The idea with derivatives is we want to be able to figure out at any possible x value. So we have to do it slightly different. We're still going to use the limit formula, so that doesn't change. So the only thing that's going to be different now is if our original function is x cubed, now our x plus h function would be x plus h cubed. Okay? So in terms of our formula, we would still subtract those. So let's simplify this one out first a little bit. So if we expand out the cubic function, we could FOIL it out 3 times. We could use the binomial expansion, whichever you prefer, but it should be x cubed plus 3x squared h plus 3x h squared plus h cubed. So if we take that FOILed out x plus h cubed, let's put it in our formula now. So our limit as h approaches 0 would be that entire x plus h cubed thing we just FOILed out minus the original x cubed all over h. So just like we did before, we can see that our x cubes cancel, which they should. We should only have h terms, and now we're going to divide by h. What I'm going to do is I'm going to rewrite this slightly different. So let's break it apart into separate fractions. So we'll have still our limit as h approaches 0. So we'll have our first thing divided by h, the second term divided by h, and our last term divided by h as well. So if we simplify that, we can cancel out an h out of each set. And now when we go to do our limits, you can see what happens. So we get limit as h approaches 0. We just get 3x squared for the first term, 3xh for the second one, and then h squared for the last one. So now when we plug in our 0, 3x squared is good, that one becomes a 0, and so does that one, because the h makes each of those terms 0. So our final answer, our final derivative, is just 3x squared. So what happens is when we deal with these limit rules and we're dealing with a polynomial, you can see that when we do our expansion, the first term cancels. Our second term, the only one that has a single h value, ends up being our final answer. Because once we cancel out the h's, it's the only thing left behind. All the rest of them turn to 0 due to the limits. So our derivative shortcut is basically going to be, can we do the binomial expansion for the second term only? So if you wanted to remember in Math 30, we could do the second term. So for like this one, it would be NC1, like if we had our expansion was say x plus h to the power of n, you'd have x nc0, x to the n, h to the 0, and then you'd have nc1, x to the n minus 1 times h to the 1, but once we put the h of 0 in and divide the h's out, that goes away. So what ends up happening is our second term of the expansion simplifies down to nc1 x to the n minus 1. So for this specific example, if our equation was y equals x cubed, and we plug it into this formula above, we bring the n down, so it'd be 3c1, which is just 3, and then we'd have x to the 3 minus 1, which is 2. So you can see that that gives us our final derivative answer. Really well for polynomials, let's see if it works the same when we do square roots. So this next example has the square root of x, so again we can plug it into our original equation. So we'd have, I'll just write the formula out this time. So we'd have the limit as square root of x plus h minus the square root of x all over h. This one we don't FOIL, but we could rationalize it. So let's multiply it by the opposite on the top and bottom. So that root x plus h plus root x. So now you can see when we FOIL out the top, we'll get just x plus h for the square root part, because those cancel, and the middle terms would cancel, and then x times x square rooted would cancel as well. So all of that simplifies quite nicely, and we're good to go because we can, on the top, x minus x cancels, and you can see we have h divided by h. So all of this should simplify quite nicely down to 1 over square root x plus h plus the square root of x. So now if we plug our 0 in, just like we normally would, that would give us an answer of 1 over root x plus root x, or we could simplify that to 1 over 2 root x. And that should be our final derivative. So before we finish this question off, let's go back and compare it to the last one. So the last one we said it was the second term of the binomial expansion. Well, we're not doing a binomial expansion here, so does that mean we need a new rule, or could we still use the same idea? So remember, our idea was if we had something like y equals x to the n, we would bring that n down in front, because that would be nc1, which is just the n value. So our derivative would end up being bring the n down, and then we'd have n minus 1 as our power. So that worked for the polynomial, so does it work for a question like this? It doesn't look like it because we don't have this n minus 1 idea, but let's see if we could apply it a different way. So if we took that original equation and we rewrite it as y equals square root of x, but instead of writing it as square root of x, if we write it as y equals x to the 1/2, we might be okay. Because if we take this now let's apply it to this formula. So our derivative would be n, which in this case is a half, x to the n minus 1, so half take away 1 would be negative a half. So that's what we would get using that little shortcut we just figured out, but does that match our answer that we actually got when we did limits? And yes, indeed, because the x to the negative half is the same thing as the square root on the bottom of the fraction. So those two things are exactly the same. So the nice part is it looks like this rule is going to work for square roots as well, not just polynomials. Okay, once we do have our slope or our derivative calculated, remember that's just the slope. So whichever formula we use, let's just use our original one, 1 over 2 root x. Remember that's our derivative, which gives us the slope. So now if I want to actually calculate the slope when x is 4, plug the 4 in, so our slope value would be 1 over 2 times 2, or a quarter, would be our final slope answer. Now if we want the equation, just like we did before, whether it's a normal line, tangent line, whatever, plug it into y equals mx plus b. So we just calculated our slope to be a quarter. X was 4 in this case. So the only other thing we need to know is what's our y value. Again, we're just trying to figure out when x is 4, so put that back into the original equation. So our y value would be square root of 4, or 2. So if we simplify this, we get 2 equals 1 plus b. Bring the 1 to the other side, b equals 1. So for this equation, doing the derivative was pretty quick. We knew that our answer was 1 over 2 root x. Plug in our x value, and that'll give us our tangent equation quite easily. So it should be a quarter x plus 1. And if I was asking for the normal equation, do the exact same thing. Flip your slope to the reciprocal, so it'd be -4, and then do the same y equals mx plus b. So one more, let's do one more quick one just to see if it works as well. So this one, we saw that it worked for polynomials. We just saw that it worked for roots. Let's see if it works for fraction equations. So now we have 1 over x squared. So let's do the same thing quickly. So we plug in 1 over x squared. That would be 1 over x plus h squared minus 1 over x squared all over h. Now we have to FOIL or common denominator it out. Let's do the common denominator first. So let's times the first one by x squared. Let's times the second one by x plus h squared. And let's simplify that. So our top fraction would be x squared minus x plus h squared all over both of those terms, all over h. So that's good. Now let's FOIL out the top and simplify that as much as possible. So the x squared will stay the same, and if we FOIL out the brackets, that would be x squared plus 2xh plus h squared, and the rest of it would stay the same, so I'll just keep working on the top. You can see x squared minus x squared cancels, so we would get, don't forget about the negative, that goes on everything, so we'd get negative 2xh minus h squared on the top all over the bottom. And let's do our reciprocal, so let's times it by 1 over h. So again, you can see our h's would cancel with one of them on each on the top, and that should be it. So now our limit, let's simplify all of this, we would just get minus 2x minus h on the top over x squared and x plus h squared on the bottom. So now if we plug in our 0, it should simplify to just minus 2x on the top, and we'd get x squared times x squared on the bottom, which we could simplify to x to the 4th. So minus 2x over x to the 4th should be our final answer, but let's go one more step. We can cancel out an x out of the top and bottom. So our final answer should be just negative 2 over x cubed. So that's what we get by doing the limits. Once again, let's try our shortcut. So I'll just do it off to the side here where I got a bit of room. So remember our shortcut would be to take this and write it as a power. So 1 over x squared would be the same thing as x to the negative 2. So now if we try our little shortcut, bring the power, which is negative 2, that would be negative 2 out front. And then we would subtract our power by 1, which would be negative 2x cubed. And you can see that gives us the exact same thing. We can actually avoid doing the limits. So our first main rule for derivatives is called the power rule, and it does exactly what we just did. So as long as we can write our equation as a power, so our equation has to be written as y equals x to the power of something. The nice part is the n can be a whole number, it can be a negative, it could be a fraction, it could be a decimal, it could be anything. As long as it's x to the power of something as a number, we can use this shortcut. So the rule or the power rule that we're going to use is if it's x to the n, bring that n down in front, drop your power by 1, and we're done. So this first example I have on the screen, bring our 8 down, drop it to a 7, we're done. Our second example, bring the negative 12 down, drop your power to negative 13. Remember, you're subtracting, so the negative would get bigger. If I gave you something like a square root, let's do x squared and let's cube root it. So again, we would have to write it as a power, so that'd be x to the 2/3. So now our derivative would be 2/3 x to the negative 1/3, because 2/3 take away 1 gives you negative 1/3. So the nice part is this rule works for pretty much anything. If I gave you some kind of weird decimal, so let's suppose I gave you x to the pi, or 3.14, our derivative would be 3.14 x to the 2.14. So it doesn't matter what the values are, the rule works for any example. So the only thing we got to look at now is what happens if it's not quite in that format. So the next thing is if we have a coefficient in front. So you can see instead of it just being x to the power of something, we've got a value in front, some sort of coefficient. The nice thing is that doesn't affect our derivative at all. We just basically leave that coefficient alone and we end up multiplying it. So you can see here the n would come down in front, so we get n times c, and then the rest stays the same. So for this example I've got on the screen, our coefficient, think of it as being a 1, so bring the 1 down in front, so 1 times 12 is 12, drop our power to a 0, which x to the 0 is just 1 anyway, so our derivative would just be 12. We don't need to write the x value at all. Okay? If I gave you something like y equals 12x cubed, it works the same. Bring the 3 down, but now it's 3 times 12, and then drop the power by 1. So this last example I've got on the page, you can see it looks different, but again, we have to write it as a power. So the only thing we would want to do is rearrange the equation to make it y equals. So if I go 4 divided by x cubed, that's not a power, so again we have to rearrange it to make it 4x to the negative 3. Now this is just like the examples we just did. Bring the negative 3 down, so that'd be negative 12x to the negative 4. So let's try this a couple more times, but let's apply it when we add or subtract. So we've only had one term so far. What's nice about the power rule is it doesn't matter how many terms. If we're just adding or subtracting, we just basically apply it to each one. So if I gave you something like 3x squared minus 6x plus 2, our derivative would be, power rule on the first one would give you 6x. The next one, bring the 1 down, would give you negative 6, x to the 0, which we don't need to write. And on a 2, when we have just a constant by itself, we could think of that as being 2x to the 0. So when you bring the 0 down, 0 times 2 is 0. Doesn't matter what happens after that, it's just 0. So we're done. So the derivative of a constant term just becomes 0. So let's try these next two. They're the same thing, just we get some fractions. So it's good to practice the fractions. So for the first one, we'd have 7 quarters, bring it down, multiply it by 4, which would give us 7. 7 quarters take away 1 is 3 quarters. The next term, do the same thing. Negative a half times 2 would be negative 1. Negative a half take away 1 is negative 3 halves. And that's it. The last one, do the same thing. 6 times 1/6 would be 1. Drop your power to a 5. And the next one, 1/2 times 3 quarters is 3/8. Drop your power to negative 1/2. So our last thing that we're going to look at before we quit this lesson is what happens if the equations are being multiplied or divided or have powers or something like that. So the power rule works really good, but it has to be single terms added or subtracted to the power of some numbers. So for now, and this even works well later, but for now we're going to simplify these first before we try to do the derivatives. So what we're going to do is we're going to take these equations and try to simplify them. So if they're being multiplied, let's just FOIL it out and multiply it. So 4 times 3 is 12. X times x to the 4th would be x to the 5th. Now that we have it as a single term, we can do the power rule. So 5 times 12 is 60, x to the 4th. So we just have to do a little bit of simplifying first. So simplify the equation to turn it into a polynomial, and then we're good after that. We don't need to do any more work. So for the second one I've got on the screen, it's a division question, but because there's only one term on the bottom, we can simplify by dividing out each term separately. So this would be like 6x to the 5 divided by 2x squared, and then minus 4x to the 4th divided by 2x squared. So if we simplify each of those, we get 3x to the 3, right? Divide and subtract your powers. Divide our numbers, subtract our powers. Now this is just a regular polynomial, so bring the 3 down. 9x squared would be the derivative of the first term. 4x would be the derivative of the second term. Okay, So that's it for that one. If we get anything that's in brackets where we see it looking like this, for now our only method really is to FOIL this out. So we could either write it out 3 times and FOIL it out, or you could use the binomial expansion and do that. I'll just keep going with the FOILing out since I've already started anyway. So let's FOIL out the second 2, so that would be x squared minus 4x plus 4. And now let's FOIL that with the first one, so that gives us x cubed minus 4x squared plus 4x minus 2x squared plus 8x minus 8. So I wrote it kind of separate here because the top row is the first one's multiplied, and then the bottom row is all of the -2 multiplied. So now if we simplify that, it's kind of nice to line them up like this. So we get x cubed minus 6x squared plus 12x minus 8. Now it's a regular polynomial after it's been FOILed, so our derivative is pretty easy. 3x squared minus 12x plus 12. And that's it. So you can see with derivatives, even though it takes a bit of work of simplifying and doing the derivative, it's still a lot faster than doing limits. So for all of these questions that we've done today, we could have done them as limits and rearranged and canceled our h's and all that stuff that we did before. This method now just gets us to that answer a lot quicker and a lot easier. So we'll stop there and we'll move on to our new topic in the next lesson.